We're talking about solving systems of simultaneous linear equations, algebraic equations, like these three equations and three unknowns up here. Maybe in high school you learned one method of doing that. I'm not going to go through this in detail. But what you do is, say, multiply a given row and add it or subtract it to another row to sort of one by one get rid of variables until you're just down to one variable. Like, first of all, I could have, I guess, multiplied this second row by 2 and subtracted it from the first row, and multiplied by 5 and subtracted from the third row. I think I get this. And now I've got two of the three. I'm done. I've eliminated one of the variables. And yeah, I'm not going to go through the rest, but do something. I forget what I'm doing. But I could have got one of these equations down to, it's just got one unknown in it, so you can solve for that guy. And then once I have this x sub 2, I can solve for x sub 3 from this equation. And then once I have two of the three, I can solve for the third. It's kind of tedious. That's the old-fashioned way, maybe the way you learned it in high school. We're going to do something similar by doing row operations on matrices. The operations we'll be doing on A and B, or maybe A and B simultaneously. We'll get into that in a minute. Here's the three types of operations we allow. To swap two rows, just swap them. Row scaling, which just means you multiply a whole row by some number. And then this is the big one that just showed up in the previous chart. You add or subtract a multiple of, say, the ith row to the jth row, and then you replace the jth row with that result. So you can kind of keep track of operations. I've given these names. Rij for swapping row I and j, Ri by multiplying row I by C, and then this thing, replacing row j by adding C times row I to. Here's kind of a neat thing. Each of these row operations can be achieved by a matrix multiplication. Here's the 3 by 3 case. If I had some matrix, say A on the right of this guy, that had 3 rows, then this would be a compatible multiplication. And this matrix would switch the first and second row of the A on the right. This matrix would multiply the second row by C. And this matrix multiplication, to an A on the right, would change the second row by adding C times the top row to it. You could do it. You could come up with whatever the matrices are for higher dimensions if it's more than 3 by 3. They're all some modification of the identity matrix. That's kind of neat. A row operation can be carried out by a matrix multiplier. Another nice thing about each of those matrices that in effect do a row operation have inverses. You can prove that here's the inverses, but what the inverse kind of does is undoes the operation. So if this matrix here was the rows, the thing that swapped rows 1 and 2, I swap them again, I get back the original. So you kind of show that this is the inverse of this matrix. Same as here. If I first multiply by C and then divide by C, I get back the original. If I first added C times a row and then subtracted it, I get back the original. So it's nice that they have an inverse, because what we're going to do, here's the equation we want to solve. Each row operation is a matrix multiplier. and say I had R row operations. E1 is the first row operation, E2 is the second, etc. And I do the same thing on the right side. So everything's equal. I still have the equal sign. I'll combine all these E's into one big E, which means the result of all the row operations. And I have this equality. I want to get this right side. Actually, no, I actually want to get the left side into a matrix of a certain format. We'll talk about that in the next video. Once I have that guy, I could, because all these guys have inverses, so does their product, I could find the original A from that resulting U. Anyway, one fact about that, if the only row operation you do is that row addition thing, the A could be broken up into a lower triangular matrix times an upper triangular matrix where all the diagonals of L are ones. In fact, it might come in handy later, I'm not sure. Anyway, we'll continue along this line of thinking in other videos.